In this short video, I'm going to explain a very important concept in statistics. It's the concept of sample variation. Well, sample variation very easily leads into a second concept, sample variance, and a third concept, one you probably have already heard about, sample standard deviation. So I'll spend quite a bit of time explaining sample variation, and then very briefly we'll talk about how that relates to variance and standard deviation. These concepts are essential for linear regression and analysis of variance. So we start with a pretend scenario. We imagine that 2 years ago, thousands of tree seedlings were planted in a large open field, and we would like to see how tall the trees are on average after 2 years of growth. So we don't want to measure the height of every single tree. So instead, we measure the height of 5 randomly selected trees. So that's where the data comes from. So here's our scale. It's going to be tree height in centimeters, and this is our sample. So the key feature of this sample is that not all trees are the same height. In other words, there's variation. So the word variation simply means not all data points are the same. So conceptually, it just means not all the same. So what is the cause of this variation, you might ask? Well, the variation is due to individual differences. So we know, for example, that for the population of all trees, there's going to be a mean height after 2 years of growth. But there's also going to be variation because not all trees are going to grow that same amount. This variation is due to differences. Differences in the soil quality or the water availability or the sunlight at different locations. So part of the whole idea behind statistics is it provides a way to quantify and to account for this kind of variation. So again, conceptually, variation just means the data points are not all the same, and variation is due to individual differences. Now we want to quantify variation. In other words, we want to have a number that tells us how much variation there is in our data set. And so one reason we would do that is often we find ourselves wanting to compare two data sets and to determine which data set has more variation. So in order to do that, we have to have a way to quantify variation. So that's what we're going to talk about here. So the first step to quantifying variation is to simply calculate the sample mean. So the sample mean would be all the data points added together divided by the number of data points. In this case, the sample mean is 48 centimeters. The second step is to calculate the deviance for each measurement. So what is deviance? Well, that's simply the distance between an individual measurement and the sample mean. So check it out. For the first data point, 20 centimeters compared to the mean, we go 20 minus 48, we get minus 28 centimeters. That's the deviance for that first measurement. So 20 is a measurement, 48 is the mean of the sample, the mean of all measurements, and we get minus 28 as the deviance. So it's negative because the measurement is to the left of the sample mean. So we can put that in a table, and then we can repeat the process for all 5 measurements. So for the second measurement, we go 30 minus 48, that's minus 18. Then we go 50 minus 48, that's plus 2. In this case, the deviance is positive because the data value is bigger than the mean. It's to the right of the mean value. Likewise, for 60, we get a deviance of plus 12 centimeters, and for 80, we get a deviance of plus 32 centimeters. Now, one thing to notice about all of these deviances is that when you add them together, you get 0. And the reason you get 0 is because the mean value is the center of all the data. And so the deviances to the left must all be the same as the deviances to the right. That's sort of what it means to be a mean value. And so you might have thought one way to quantify the variation would be to add up the deviances. But if we add them up, we get 0. And so Adding up the deviances is not a good way to quantify variation. What we need is a way to get rid of the minus signs. And now that's actually quite easy, because what we actually do, is we square the deviances so that all the negative signs disappear. So it looks like this, here with a new table. We're going to sum the squared deviances and use that as a measure of variation. So here we have our deviances. Here are the squared values. Notice they're all positive, and so now when we add them together, we get a non-zero value. And so here, the sum of the squared deviances is what we use to quantify variation. In this case, the variation of this data set is 2,280 centimeters squared. So the sum of the squared deviances measures variation. The sum of the squared deviance is often called simply the sum of squares. So we use the sum of squares to measure the variation of our data set. And in fact, when we write this down, we use an abbreviation. We just use SS. SS represents sum of squares. You're going to see this abbreviation when you look at Minitab output for regression and for analysis of variance. And so now you know what that number means. It's the sum of squares. Now notice what we did to calculate this sum of squares. First, we calculated the deviances. A deviance is just the difference between an observed value and the mean of all the values. And then we squared that number, and then we added all those values up, all of the squared numbers up. So the sum of squares is just the sum of all the squared deviances. This equation here is essentially instructions for how to calculate the sum of squares. I hasten to add that for your purposes, you will almost certainly never have to calculate the sum of squares. What will happen is you'll be given a scenario and Minitab output, and you'll have to recognize in that Minitab output which numbers are the sum of squares. And you have to understand how to make use of those numbers to calculate other things. So you don't need to worry about how to calculate this, but understanding how it's calculated helps you understand what it actually means. So let's just put that to the test. Here we have two data sets, and we're going to ask which of these data sets has the larger variation. Now there's two ways to handle that. One way is to actually calculate the sum of squares for each data set. Another way is to use a bit of reason. So for the first example I'm giving you here, we're going to do the calculation. Right. Notice that both of these data sets have the same mean value. And let's calculate the sum of squares for each of these two data sets. The first data set is easy because we've already done the calculation. For the first data set, the sum of squares is 2,280 centimeters squared. For the second data set, all we need to do is take each of our measurements, subtract the mean value. That gives us our deviances. We square each of those deviances, and then we add them all together. And when we do that, we get 2,494 centimeters squared. So notice the second data set has smaller variation compared to the first data set. Now, why is that? Let's sort of look at the nitty-gritty a little bit. So you notice that the two data sets are mostly the same. The first tree is the same, 20 centimeters tall. The tallest tree is 80. The second tallest tree is 60. The only difference between the two data sets is that in the first data set we have a 30 and a 50. In the second one we have a 25 and a 55. So these two data sets have different variation solely because of the difference between these two values. So in the first data set, looking at the 30 and the 50, we'd look at the deviances, we look at the squared deviances. These two data points contribute 328 centimeters squared to the total sum of squares, right? 328 is just 324 plus 4. What we're going to see is that when we look at data set B, these two data points contribute more to the total sum of squares. And why is that? Because these two values are further from the mean compared to their counterparts in the first data set. So looking at these two, we can see essentially it's as if this tree was replaced by a tree that is a bit smaller, and the second tree was replaced by a tree that was a bit bigger. We basically moved these two measurements further away from the mean. That increases the spread of the data. And what's the consequence? These two data values have larger deviances and therefore larger square deviances. And so in this case, these two measurements taken together contribute 578 centimeters squared to the sum of squares. In other words, 529 plus 49. So that's much larger than the contribution to the sum of squares for these two data points. So what conclusions can we sort of draw? What generalizations can we draw? First of all, let's remember what we're talking about. The sum of squares measures variation. This gives the instructions for how to calculate the sum of squares. We just calculate the deviances for each data point. We square those values and then add them up. And so what we sort of, hopefully you understood from the example, is that if you move a data point further from the mean, that increases its deviance. And this results in a larger sum of squares. So in other words, the more spread out the data is with respect to the mean value, the greater the variation. Okay, so now I'm going to put it to you. Here we have two data sets that are slightly different, and I'm going to ask you to think about which of these data sets has the smaller variation. You can pause the video for a few minutes. Think about the answer to the question. No calculation is necessary. You should be able to reason it out. Just pause the video, take a few minutes, and to come up with an answer. Okay, so hopefully you noticed that the only difference between these two data sets, they have the same mean value. They actually have the same range. In other words, the difference between the largest and smallest value is the same for both data sets. The only difference is 30 has become 32, a little bit closer to the mean, and 60 has become 58, also a little bit closer to the mean value. And so moving these two data points closer to the mean is going to reduce their deviances, which has the effect of reducing the sum of squares. So it's data set B has the smaller variation because it has two measurements that are closer to the mean value compared to data set A. Okay, let's try one more of these. This one's a little bit more complicated, but again, you can still reason which of these two data sets has a larger variation. You can reason it out without calculating. Pause the video and think about that for a few minutes and try to come up with an answer. Okay, so this one's a bit complicated because the data sets have different mean values. But what you'll notice is that these first four data points are very similar, in data set A rather, are very similar to the first four data points in data set B. The differences are quite minor. The big difference between the two data sets is this last tree. It went from 80 in data set A to 90 in data set B, which is quite a bit larger. And in fact, if you compare the range of the two data sets, the first data set, the difference between the largest and smallest is 60 centimeters. In the second data set, it's 70. So there's a larger range. Well, remember, the sum of squares is a measure of the spread of the data. The range of the data is another way of measuring spread. It's less sophisticated, but it is a way of measuring spread. The second data set clearly has more spread than the first data set, and therefore it's reasonable to conclude that it will also have a larger variation. And in fact, that is the case. The second data set does have a larger variation compared to the first. Right. I meant to mention earlier, yes, one of the salient features in this example is that the means are different, but that doesn't matter. We can look at the spread of the data to make our comparison. So data set B has a larger variation because it has a greater range. That is the largest value minus the smallest value compared to data set A. Great. So that covers sample variation. Sample variation is measured by the sum of squares. Now let's move on to sample variance. This is going to be quite easy now. The difference is very slight. The variance is just the mean sum of squares. In other words, it's the sum of squares divided by something called the degrees of freedom. This degrees of freedom depends on the context. In other words, it depends on the statistical model that you're looking at. In this present scenario, the degrees of freedom is just 1 minus the sample size. So, in this case, the mean sum of squares is just the sum of squares divided by 1 minus the sample size. And so we get 570 centimeters squared. So the variance of this data set is 577 centimeters squared. The variation is 2,280. The variance is 570. So let's just summarize that. Variation is measured by the sum of squares. It's the deviances squared, and then you add them up. So this is the instruction for calculating sum of squares. The variance is just the mean sum of squares. So it's the sum of squares divided by the degrees of freedom. This degrees of freedom will change depending on the context, but in this context, it's just the sample size minus 1. Again, I do hasten to add, these calculations you will not have to do yourself, but you will be given Minitab output, which displays a sum of squares and a mean sum of squares, and you need to understand the difference. And when you learn things like regression and analysis of variance, ANOVA, you will learn how to make use of these measurements. Right, so the sample variance is just the mean sum of squares. Now let's go on to the sample standard deviation. You have probably seen sample standard deviation in a previous course. So this is going to look familiar to you. What is the sample standard deviation? It's just the square root of the variance. And so the sample standard deviation is the square root of that variance that we calculated previously. Notice that the standard deviation has the same units as the individual measurements. That's one of the things that makes standard deviation a very convenient way to measure the spread of your data. And so that's pretty much it. Let's summarize once more. So variation is measured by sum of squares. Variance by the mean sum of squares. And the standard deviation is the square root of the variance. And so looking at this last formula, you may well have seen this equation before, but probably you didn't understand it. And I don't blame you. It's a complicated expression. So by breaking it down, starting with sum of squares, and then moving towards standard deviation, hopefully this gives you a better understanding about what these things are measuring. In the end, all three of these are different ways of measuring the spread of the data in your sample. Good. So, finally, let's just remind you, these concepts are essential for understanding linear regression and analysis of variance. And so it's worth taking the time to really understand this concept, especially the concept of sum of squares. So if you need to, watch the video a second time. If you have any questions, leave a question in the comment and I will get back to you. Thank you for listening, and bye for now.